start recording thing. So yeah, you don't have to, so you guys won't be here at all for, if you're a junior, you'll be here on Tuesday taking the U.S. history class, but none of you guys will be here Wednesday for the ninth graders taking the STAR EOC test. All right. Any other questions before I start asking you questions? All right. So we've got some evolution, cladograms, Hardy-Weinberg stuff that we're looking at today. So I've got one cladogram question. If you're in the after school reviews, we did like 2 or 3 of them or something like this. So I'm starting to run out of old cladogram questions to ask you. But because they ask it almost every year, I can't remember exactly what it was. I said it a week ago when we were talking about cladograms, but like from 2019 back to like 2013 or 2014, they ask a cladogram question every year except for like one, I believe it was. So the likelihood that you see a cladogram is really good. 2020 was a weird year because it was COVID year. And so that one doesn't really count as far as like the format was different. So I don't factor that in. So let's try this one. Have you guys seen this one or do you know? I don't think you have. There's another one that I had, but I think I showed it to you the other night. Have you guys seen that one? Okay. All right. So let's try this one. This is in our updated version of free responses. So if you're at home and you don't want to look at my screen, if you want to like see the actual file, if you go to AP Bio, I'm sorry, if you go to our Google Drive, AP Bio, Notes, Unit 8, it's in there and it's updated. So I just updated it this morning. So this one says this. Question 3 in 2015. So in 2015, question 3 was worth 4 points, just like this year. Question 1 and 2 will be 8 to 10. And then question 3, 4, 5, and 6 are all 4-point questions. So this one says, the number of amino acid sequence of cytochrome C was determined for 5 different species of vertebrates. The table below shows the number of differences in the sequences between each pair of species. All right. Using the data in the table, create a phylogenetic tree. Phylogenetic trees and cladograms, again, for us, we just use them as synonyms. Technically, a phylogenetic tree is who evolved from who. A cladogram is what characteristics do they share in common. So usually they're the same. Usually I look a lot like my brother because I'm related to my brother. Usually I don't look a whole lot like somebody that I'm not related to because I'm not. But every once in a while, things look similar, even though they evolved completely separate from each other. So create a phylogenetic tree on the template provided to reflect the evolutionary relationships of the organisms. And then provide reasoning for the placement on the tree of the species that is least related to the others. So let me scroll down there so you can kind of see the tree that you're going to draw on. Something like that. And if you're at home, if it's hard to read like the actual names there, then you can just call this like the first one, the second one, the third one, the fourth one, and the fifth one. I might be able to zoom in just a hair more and still fit it on there. On free responses, you're supposed to write mostly in a dark pen like blue or black ink. It's easier to read when lighting is poor, but you can use pencil, especially if you're doing something mathy and you want to use a pencil, you can. So they don't like refuse to grade it. It just harder on your eyes. All right. So this says number of amino acid differences. Sometimes charts will say like number of similarities or something like that. So knowing whether they're similar or different makes all the difference in the world, or all the similarities in the world, whatever. So when I look at these up here, who seems to be most closely related? Looks like this one right here and this one right here only have one amino acid difference. You might at first, when you're kind of glancing through, you're like, oh, that one's three, but that one's only got one difference. So I don't remember did they even tell me what the genus was? So yeah, I don't even know what the E stands for. So E ferris and E africanus. So if I'm putting them over here, oh, where would I put them? Okay, did you say far right? Okay, so let's say I put, I'll say EF and EA, EF and EA. Okay, who's the next most closely related? Uh-huh. Yeah, the A one and the G one. So Gangsta Gallus and A Forstery. So we have like GG and AF. And then who seems to be the least related to everybody? Yeah, basically the only one left. This guy right here, DP, is like, you know, he's 18 different, 17 different, 20 different. So D and P. Okay, so let me flip cameras. It's not in Canvas. If you go to Google Drive, AP Bio, and then the notes section, it's Unit 8. So if you go into the notes section of our Google Drive and you go to Unit 8, it's a file in there called like AP Bio Free Response. And once you get it, oh, you're welcome. And once you get there, it's like way at the bottom. There's like 33 pages, and it's literally page 33. Uh-huh. Would it matter if we mix like the middle branches and like the branches on the far right, those two? Okay, so what if I do this? Or not that, but like if I put EF and EA on the middle branch. No, no, it'd be fine. Oh, okay. Yeah. So if I flip flop these two, nothing changes. Here's why. So I'm going to go through like three different changes that you could have. And the third one will be actually what you're asking about, James. So I can flip these two and it doesn't change anything because those two still share that same recent common ancestor. All right, if I flip flop these two, same thing. It doesn't matter because those two still share that same recent common ancestor. If I did this, if I did GG AF, then over here I had EF and EA, it still doesn't change anything. And the reason that it doesn't is because How do these two compare to Gigi? They have that common ancestor. How does that guy compare to Gigi? That common ancestor. How does AF compare to EA? That common ancestor. So even if I flip-flop these, how does AF compare to EA? It's still the same common ancestor. So it's the reason that it's okay is because if I compare this guy to this guy, that's their common ancestor. If I flip-flopped them and I compared this guy to this guy, that's their common ancestor. So it didn't change anybody's relationships. That one's kind of odd because there's so many different ways to write it. And then they said, provide reasoning for the placement on the tree of the species that is the least related. So this one's the least related. And the evidence for that is, well, it has the greatest number of differences in amino acids in cytochrome C. So that's why. By the way, what's that group out there called? The out group. So if you went back and looked, or for those of you that were in the after school review, out group came up probably, I think we did like 3 cladograms maybe, and they asked about the out group on 2 of them. And now they ask about the out group on this one. So the likelihood that you see a cladogram on the free response is really good. The likelihood that they somehow ask you questions about the out group is pretty good. What they haven't asked at all, and so I think it's due, is for them to start saying like, hey, here's one, here's one, are they both the same, and explain why. So basically kind of like what James was mentioning, like, hey, if I flip-flop this Y and this Y, does it matter? No. So some sort of question where they're like, hey, here's our data. Here are 2 cladograms. Which one's right? Or are both right? And then, of course, justify your answer and talk about the outgroup. So that's what I could see happening. They have in the past had 2 different ones, and they really were different, and you had to pick which one was right. But what they haven't asked is, here's one, I flip-flop some crap, and then in the end, it's like, oh, by the way, those are both correct, and here's why. Why is it okay for me to take these 2 and move it over here? Because it doesn't change who their common ancestors were. That's why. All right. The biggest mistake that students make when they start looking for relationships is they start looking left and right only instead of going back. So, okay. And then the last part, identify whether morphological data, let me flip cameras for you. Identify, and let me move myself. Y'all ever seen Austin Powers, the first one? Allow myself to introduce myself. I'm Richie Cunningham, and this is my assistant. All right, part B. Identify whether morphological data or amino acid sequence data are more likely to accurately represent a true evolutionary relationship among the species and provide reasoning. Morphological data or amino acid sequence data. Which one is better and why? So I'll give you just a minute. Then we'll see if we can kind of piece together. If you're like, well, morphological data, maybe that means this. What does that mean? Morphological data or amino acid sequence. All right, anybody want to take a crack at what you think morphological data is? Uh-huh.
I know in like metamorphosis,
Uh-huh.
it's like the change kind of like shape
Yeah.
or like I guess like phenotypic characteristics.
Yeah.
So I imagine a morphological would be kind of like what you look like in a vague sense.
You're exactly right. What you look like. So I can morph into another creature or whatever. So it's like changing shape or changing what you are. So if I'm looking at like generally characteristics of what you look like, hair color, eye color, height, skin color, are your earlobes attached or not, that kind of thing, that's morphological data. So what's probably better, that or like molecular kind of like amino acids. Amino acids. Why?
Less variables.
Yeah, there are less variables, meaning like I might have brown eyes and James has brown eyes, but it's possible that our amino acid sequences are actually different, right? So, as a general rule, the closer you get to like DNA nucleotides, that's the best evidence. And the reason for that is I might have, let's say I'm looking at a protein sequence. I've got a protein and it's like 50 amino acids long. Well, amino acid number 44 might be proline for me, and it might be proline for you. But genetically, my proline might be coded by CCC, yours might be coded by CCG. So DNA is like more specific. It's like more high resolution. It's like a 4K TV versus like a regular K TV. So DNA evidence is best. Next up is amino acids. And then as you get farther and farther and farther, and it's more visual. Basically, the smaller it is, the further back you go, the better it is. The more it's like, oh, you got brown hair and so does he. I bet you're the same. It's like, no, not really. There's a lot of people with brown hair. All right. You ready for a tough one? You ready for a Hardy Weinberg combo with chi-square essay question? That's what I thought. That's the spirit. If you didn't hear them at home, what they said was bring it on. I just got fact checked, and I was called a liar. Evolution. It is. It is data, but like it's morphological. It'd be like, yeah, like appearance and stuff. Thank you guys that are participating in the chat. All right, let's give this one a shot. Remember, you get calculators on the real test during all sections. So if you've got kind of the most common are probably 83s and 84s. So if you've got one of those, you can bring it. If you want to borrow it from your math teacher ahead of time, you can. We're not supposed to loan them to you. But if you went to your math teacher and was like, hey, can I borrow that calculator for like 2 days? I'm sure that they would allow it. Otherwise, you get one of these, kind of like a pretty simple calculator. It's all you need. As far as the advantage of this one, the only advantage is you're not going to use any more keys. The only advantage is on this one, like, once I turn it on, I've only got one line of numbers. Sometimes it's useful to be able to see like 2 or 3 or 4 lines of math if you need to. That's really the only advantage of a big one. So you can bring your own calculator if you want. I'll have a giant tub of these. All right, let's give this one a shot. Let me zoom it in here. Where did the plus go? There it is. All right, this one's tough. Imagine an isolated species of caterpillars with two distinct color variations living in a prescribed area. Scientists collected as many caterpillars as possible in caterpillar traps in a 20-day period. What have you been doing for the last 3 weeks? Catching caterpillars. Those captured were tested and genotypes were determined as shown below. Scientists returned every 10 years to collect data. Every 10 years. You got a 30-year caterpillar experiment going on here. Okay, so it should be noted that in the year 2005, a species of bird that preys on caterpillars was introduced in the area of the caterpillar population. Okay, so part A. This would be a 10-point question. Is the caterpillar population in Hardy-Weinberg equilibrium when comparing year 2000 and 2010? Justify your answer mathematically using Hardy-Weinberg equations. There's nothing about chi-square yet. Chi-square comes in on like part B. And this one is homemade. This is not an old AP question. I used to work at a company, and my boss used to write the AP Bio exam. And so he's like, "Hey, you having trouble coming up with any questions?" I was like, "Yeah, could you come up with one for this?" And this is what he wrote. So I tweaked it a little bit, but it's pretty much his. He actually wrote the test that I would have taken if I had taken the AP Bio test my senior year. Bless you. Is the caterpillar population in Hardy-Weinberg equilibrium when comparing the year 2000 to the year 2010? And then I have to, if I say yes or no, then I have to like prove it with some Hardy-Weinberg math. Oh, the Hardy-Weinberg equations, by the way, they would be given to you on the test. P plus Q equals 1, and P squared plus 2PQ plus Q squared equals 1. This is, in my opinion, the hardest free response I've ever asked you guys. Everybody's different, of course. Oh. And if you want, of course, you've got a calculator on your phone, but if anybody wants some calculators, I've got some. Anybody needs one, just raise your hand. You're welcome.
Thank you.
You're welcome. See a lot of you guys still punching away on calculators, so I'll give you a little bit longer. If you're still cruising along, that's fine. I'm going to go ahead and start walking through it, but if you're still finishing it up, that's totally cool. All right, so is the population in equilibrium or not? So what would it look like if they were in Hardy-Weinberg equilibrium?
Should add up to one.
Okay, they will add up to one. So they will always add up to one.
Like the ratios of genotypes would be the same, right?
Yeah, the ratios of genotypes would have to be the same, specifically the alleles. So technically, the genotypes could switch around, but if like P and Q change, then I'm out of sync. I'm not in Hardy-Weinberg equilibrium. So what I have to do is I have to find P and Q for 2000, and I have to find P and Q for 2010. If P stays the same and Q stays the same, I'm in Hardy-Weinberg equilibrium. And if they don't stay the same, then I'm out of Hardy-Weinberg equilibrium. So here's what we do. If I look at these at first, you'll notice the numbers actually kind of add up to clean numbers, like that adds up to 50. This adds up to 200. This adds up to 100. This adds up to 200. Okay, so if this adds up to 50 and I wanted to make it percentages, then wouldn't I just like double everything? So if I have 18 and 24 and 8, then if I wanted to make that a percentage, then 18 out of 50, this is a total of 50. 18 out of 50 is 36%. 24 out of 50 is 48%. 8 out of 50 is 16%. So it looks like my percentages in 1980 were 36, 48, and 16. Okay, they didn't ask about that. I'm just trying to make a point. In 2000, it's 36, 48, and 16. Here, these add up to 200. So 72 out of 200 is 36%. 96 out of 200 is 48%. So it looks like my numbers are every single year. It's 36%, 48, 16. 36%, 48%, 16. Every single year. When I go from 2000 to 2010, is that the case? No. So they are not in Hardy-Weinberg equilibrium. Let me prove it to you with some math. So in the year 2000, I had big B was 36. Big B, little b was 48. Little b was 16. All right, so I need to find P and Q. What does P represent, by the way? Yeah, the dominant allele. And then that means that Q represents the recessive allele. Good. So we're using letter B's. So that means that, like, that's capital B. That's lowercase b. All right. So I know that little b is 16. That means Q squared is 16. All right, well, if Q squared is 0.16, then Q squared is 0.16. So if I square root both sides, I can find Q. So Q is 4. Q is 0.4. I know that because of this. They gave me little b is 16. So that means Q squared is 0.16. And that means that Q is 0.4. All right, well, if Q is zero point 0.4, Q plus P has to equal 1, so that means P is 0.6. All right, so in 2000, Q was 0.4 and P was 0.6. All right, in 2010, here's the thing. In 2010, I didn't catch 100 caterpillars. I caught 200 caterpillars. So my numbers over here are always a percentage. They always add up to 100%. So I have to first convert this to a percentage. Does that sort of make sense? It's kind of like if I were to say, all right, in the year 2000, I was looking at Timber Creek, and in the senior class, there were 50 boys and 50 girls. All right. I want to see if the ratios stay the same. But next year, there's 100 boys and 100 girls. The ratio is the same as a percentage, but absolute numbers, it's more than 100. So I have to first convert this to a percentage. So if all this adds up to 200, then 98 out of 200 is 49%. So over here, big B is 49%. 84 out of 200 is 42%. And little b, that'd be 9%. All right, so same thing as before. Q squared is little b, so that's 0.09. That's the piece of information that I want to use. All right, well, if Q squared is 0.09, then when I square root that, you might want to think that it's 0.03, but it's not. It's 0.3. You can check it in your calculator if you want. All right, well, if Q is 0.3, I know P plus Q has to be 1. So that means that P is 0.7. So between the year 2000 and 2010, am I in Hardy-Weinberg equilibrium? Nope. Justify it mathematically using Hardy-Weinberg? There you go. All right, that was part A. Now there's part B. Now we get to bring in the chi. All right, using chi-square and the accepted, let me flip cameras for you. Using chi-square and the accepted probability value of 0.05, determine if the variation found between 2010 and 2000 is due to chance or if some other factors influence the results. Show work, box in answers. Be sure to explain what your math means once you get a final number. And then chi-square critical values are like on the next page. So we agree that they are different. Statistically, is it significant? Chi-square should let me know. So chi-square equations are given to you on the test. Chi-square is this. Chi-square equals sum of sigma, observed minus expected squared over expected. And I will flip back over to the whiteboard for you guys at home in just a second. Using chi-square and the accepted p-value of 0.05, determine if the variation found between 2010 and 2000 could be due to chance or something else. And this is the hardest part. A was tricky, but B is trickier, more tricky. Okay, now I'm going to flip back over here for you guys. I assume it's probably easier to read the typed version than my numbers here. Supposed to use chi-square and see if the difference between 2000 and 2010 is statistically significant or not. All right, so I'm going to help you through the first hurdle. If you're stuck early on, most likely. So students that would otherwise be able to get it, there's this one kind of catching point. Um, what observed and expected do I use? Like, like I want to know, it says, using chi-square, determine if the variation found between 2010 and 2000 could be due to chance or if some other factor influenced it. And I'm only going to use the chi-square equation once. I'm not going to like run a chi-square on 2000 and run a chi-square on 2010. I only run it on 1 year. Which year is it? Turns out it's 2010. So what did I observe in 2010? I observed 98, 84, 18. So I observed 98, 84, 18. 98, 84, 18. Now, what's incorrect about this? I could say, well, I expect to observe the same stuff from 2000. So I expect 36, 48, 16 again. And so I'm going to put, this is incorrect. I'm going to put 36, 48, and 16. What's incorrect about that? Why is that not logical? Yeah, it adds up to a different amount. Again, it's back to my analogy of the senior class. If last year it was 50-50, there were 50 boys and 50 girls, and this year the total enrollment is 200 in the senior class, then I don't say, well, I expect 50 boys and 50 girls. It's like, but there's 200 students. So what are the other 100 students? You know what I mean? So um, back over here, my expected has to be this percentage, but out of 200 total. So let's say I'm 50% boys, 50% girls. And then we're like, all right, next year, there's 200 in the senior class. So how many boys and girls do you expect? You'd be like, well, not 50-50. I'd expect 100, 100. What you just did in your head was what we have to do here. I expected 50-50. I expected them to be equal. So now I need equal numbers that add up to 200. If there was 1,000 students, then I'd expect 500, 500. So I do the exact same thing. I expected 36% of them to be this, 48% to be this, and 16% to be this. But there's 200 caterpillars this year. So I multiply everybody by 2. So I expected 72, 96, and 32. What did I observe? 98, 84, 18. What did I expect? 72, 96, 32. So now I can throw those numbers into my chi-square equation. How many fractions am I going to have in my chi-square? Yeah, 3. I'll have a fraction for these guys, a fraction for these guys, and a fraction for these guys. So now, the first fraction, I've got my observed of 98 and my expected of 72. So I observed 98 minus my expected of 72. I square it over my expected of 72. That guy's done. My next fraction is line number 2. I observe 84. I expected 96. Squared over 96. And then my third fraction, I observed 18. I expected 32. So I get 18 minus 32 squared over 32. And then when I add all this crap together, let me fast forward. I want to say it was 17. I was trying to memorize the number. Yeah, 17-ish. I was trying to memorize it so I didn't have to like calculator it. So if I do this, oops, I don't want to forget the squared. Once I do all that math, 98 minus 72 is like 16. I'm sorry, 26. 26 squared divided by 72. Once I do all that math, my chi-square should come out to somewhere around 17-ish. So now what do I need to do? Now I've got that chi-square critical value table. So I have to do something with this number. This is what's hard about chi-square is like we kind of use it and then like we don't continue to use it. Like once we learn about water being polar and fats being non-polar, it seems like that comes up at least a couple of times a month. Like chi-square, we kind of like do it and then we're like, all right, see you. Howdy Weinberg, we do it and then it's like, all right, that's it. So we got to kind of knock the rust off. My chi-square value is about 17. And so I have to somehow like use this chart. They told me back in the question that we're looking for a p-value of around 0.05. What did DF stand for again? Degrees of freedom. How many degrees of freedom do we have in this problem? I can tell by solely looking at the math. I don't have to read the problem at all. I can look at this and tell you the number of degrees of freedom. 2. Why is it 2?
Because there's 3 like chances or like 3 different opportunities or like options.
Yeah, 3 different opportunities or options or outcomes or whatever word you'd like to call it. I could have been big B, big B. I could have been big B, little b. I could have been little b, little b. So there are 3 genotypes, 3 possible outcomes. And degrees of freedom is total minus 1. You might remember I gave this example. Here you are, and you've got 3 pins to choose from, which one you want. And I'm like, all right, Veronica, which color you want? Blue. She picked blue. All right, you at home, what you want? Great. Orange. You picked orange. So now, when I go and I offer this to somebody, I'm like, which one do you want? It's not a free choice. So if there are 3 options, 2 are free choices. So there are 2 degrees of freedom. I know I've said it before also, but like our alphabet, it has 26 letters, so it's got 25 degrees of freedom. It's always just the total number of options minus 1. Okay, so at a p-value of 0.05 and 2 degrees of freedom, the critical value is like 5.99. My number is quite a bit bigger. My number was 17. So what does that mean if my number is bigger on this chart? If it's going this way, what did I do with that? I'd say something about my null hypothesis.
Reject.
Yeah, I reject my null hypothesis. So if I'm bigger than this, I reject my null hypothesis. Those of you guys that are in stats, who else is in stats? Is it just, okay, so for you guys, what you do is slightly different. Have you done chi-square now?
We're
Okay, so one thing that you'll do in stats is you won't just say, is it bigger? She will then have you estimate, and she'll have a bigger chart, but she'll say, find 17 and find it on the chart, and then you'll talk about the p-value. The way that you'll say it in stats is you'll say, our p-value is like less than 0.05, and therefore we reject the null hypothesis. Okay, what was it if it was going this way? We don't say reject. We say we fail to reject. We're not supposed to say we accept. We fail to reject. If you want to know why, go down the hall a few doors. I'm sure you could talk about it for a while. What it comes down to, though, kind of a quick version, is just like law, and I gave this example earlier in class, it's just like law. I don't have to prove my innocence. It's just I'm either guilty or not guilty. That's different from innocent. If you don't have enough to pile on me and throw me in jail, then I'm not guilty. That's different than like failing to reject is I have a hypothesis. Have you got enough data to knock it down? No, not really. That's different from like I accept your hypothesis. That's like, yeah, I can't really disprove that. Anytime you're trying to argue some case in life, you need to remember that. Like, do you have enough evidence to like knock down whatever somebody else is saying? So I think they're riding roller coasters over there or something. I don't know. All right. So what we would say with this one is because my number 17 is larger than 5.9, I would say that I reject my null hypothesis. Um, if you're in a stats class, you'd have to go a little bit further and say something like, I reject my null hypothesis. The differences between these are likely not due to chance. There's probably some sort of outside force at play. Speaking of outside force at play, what was the most likely influence in the results? Yeah, they introduced a bird in 2005, a species of bird that preys on caterpillars. So I think that that bird is eating certain colors of caterpillars over others. It's set up here that there's two distinct color variations. So maybe one of the caterpillars blends in with the surroundings more. Maybe it's green and there's always green grass. Or maybe it's kind of tan and it's always amongst some like kind of dead grass. Maybe it's always kind of wintertime or something like that. So it was probably the bird. All right. And then part D. Suppose you come back in the year 2050. You've now been studying these caterpillars for 70 years. 70 years. And you probably didn't start something like this until you were at least in your 20s. So you're like 90 something. And you're still doing this freaking caterpillar experiment. So suppose you come back in the year 2050. The predatory birds have been present since their introduction in 2005. Predict the fate of the recessive allele and justify it. So, will the recessive allele be more common, less common, or gone? And then justify. So take just a moment. This will be the last thing, and then I'm sure the song will come on, the grunge song. That's spot on, and you know it. Wait, you're telling me they didn't just come on and play the song? Yeah, see, there you go. The only reason you could tell is that was pure a cappella. There was no other like musicians in there playing the guitar or the drums or anything. All right, so do you think the recessive allele would be higher? Well, of course not. Do you think it would be lower or zero? Why is it not going to be zero ever, most likely? This comes down to a fundamental question in genetics. Why do we never evolve out of really rare recessive diseases? Why are they always around? Tay-Sachs kills everybody by like age 7 or 8. How is that still here? How hasn't that extinguished itself in a single generation? You can't reproduce until you're in your teens. Why is Tay-Sachs still around? Why are really rare recessive disorders always hanging around? Why don't they extinguish, go extinct, basically? Sounds pretty good. Yeah. If I had half a mouthful of water, I'd be a little bit closer. Okay, both of you guys went up. We'll give it to James first.
Mutations, like even if it went extinct, would it like mutate back into existence?
That's true. There's always mutations that could happen. That's true. So, barring mutations, but you're right. Like, mutations can always happen. So, something could always come back in. Hey. Oh, awesome. Thank you very much. Good to see you, by the way. Wonder who that's checked out to then. All right. What do you think, Travis?
Because it's going to be the heterozygous keeps it going.
Yeah, heterozygous keeps it going. So why doesn't Tay-Sachs go away? Because mama could be, let me flip back to this camera. If big N is normal and little n is not, mama could be big N, little n, and she's alive. Dad can be big N, little n, and he's alive. But then there's a 25% chance that their kid would have Tay-Sachs, little n, little n. So really rare recessive disorders, we don't evolve out of them typically, unless they become so rare that there's like 4 people carrying it and then they die or something. But usually they hang around because heterozygotes keep them around. So that's why we would expect the number for the recessive allele to be lower, because it keeps getting lower. Um, but we wouldn't expect it to be like totally gone. So, all right, let's see what we got on TCTV. If you're on Zoom and you have questions, feel free to stay on. If not, you are free to go. See ya. Hope to see you tomorrow after school.